All right, everybody, we are getting into the second derivative test now. So what I need to talk about first is what does the second derivative look like in relationship to the original function. So we know, let me think about the best way to do this. I probably should have done that before I started the video, huh? Yeah, probably. All right, but let's say I have my cubic function something like this, right? This is my graph of just f, just regular f. My graph of f prime is going to have zeros when I have a horizontal tangent, and it's going to be increasing, decreasing, and increasing. So I'm going 0, 0. Decreasing would be negative slopes, increasing would be positive slopes. Right, so I would have a function something like that. This is my graph of f prime. So now if I take f double prime, right, that's just my derivative of my derivative. So I can apply the same logic. So f double prime is going to have zeros when f prime has a zero, which is right here. And I am going decreasing and increasing. So the slopes there would be from negative to positive. Right, so that would be the graph of f double prime. So let's see how they relate. Well, what they do is, let's see, my 0 is here, which is about right here for my graph of f. So looking at my graph of f, kind of the change that happens is the part of my graph right here is curved down until I hit this point, right? I'm curved down. That's called concave down. And then it goes the other way. It curves the other direction, such that I am concave up. This position right here, where it is changing concavity, is called a point of inflection. And that happens when f double prime of x is equal to 0. As long as, right, it goes from negative to positive. The times that it will not change at a point of inflection, concave up to concave up. What would that look like? I can't think of anything right now, but maybe going through it, we will come up. But for the point of inflection, right, if I have x equals c, and I'm relating f double prime to f, if I go positive and positive values on either side, this is concave up and concave up on both sides. So it would be like shoo, shoo. Shoo, shoo. So it might not be, I'm not sure. That's where I'm kind of struggling, because it might be a point of non-differentiability. It may come up. But we do have to check that there are points of inflection, just like with the first derivative test. We have to check whether they are really maxes or mins as well, right? We have to check that these point right here and this point right there were a max and a min using that first derivative test. So the second derivative test is if my second derivative is greater than 0, then I know my function is concave up, right? And that's what we were talking about over here as well, right? My outputs were greater than 0 for my second derivative, so that part of my function was concave up. If I have negative values for my second derivative, that part of the function is concave down. Okay, so using these, we can also determine maxes and mins. So given the fact, erase a few things. given the fact that f prime is 0 here, and I am concave down on that interval, that means that if I am concave down and f prime was 0, that had to be a relative minimum point. So let's just get into an example and we will see how this works as well. So determine the intervals on which each function is concave up or concave down. Find any points of inflection. So I'm going to want to talk about the second derivative. So I will take the first derivative in order to get to the second. That's nice. All right, because then if I set it equal to 0 to figure out where it's changing my concavity, then x would be 5 over 3. So that means for my function, for f double prime, relating it to f, at 5/3, if I plug in 0 and 10, say, to my second derivative, 0 would be negative, which means that f would be concave down, so I have a graph that would look something like that. At 10, it would be positive, so I would be concave up, so it would look something like that. Since this is for sure changing concavity, x equals 5/3 is a point of inflection. And let's see, is that easily factorable? 3x, 3, 9, 1. Yeah, I think I can factor that. Sorry, I got distracted. But since I'm changing concavity, 5/3 is definitely a point of inflection, right? And I can tell the intervals where it is concave down, where it is concave up. So what I want to do is, it's not a part of the problem, but let me finish answering the problem. Determine the intervals on which it is concave up, concave down. So concave down on the interval from -infinity to 5/3, because f double prime of x, I'll just say f double prime, they'll be fine with that, is less than 0. Concave up on the interval from 5/3 to infinity, because f double prime is greater than 0. Point of inflection, at x equals 5/3, because f double prime goes from negative to positive. All right, this would be how you would answer this question. So here's how we can actually use this more to help us with these functions as well, which I'm sure we're going to get to. I have no doubt. Yep. But with my function, right, my first derivative was this. So if I set that equal to 0 and factor, then x equals 1/3, x equals 3 are my two extrema points, maybe. Right? I do need to verify that. So if I have f prime and f, my candidates are 1/3 and 3. So I would want to check like 0 or something, and that would be positive. So I have increasing, and I could check like 2, which would be negative. So I have decreasing, and I could check 10, which would be positive. So I have increasing. All right, so now using these facts that I have, I can come up with a pretty good graph of what this would look like without really knowing what it would look like. Right? I'm also given the fact that f of 0 is 9, just using my y-intercepts. I don't know my x-intercepts. I'm not too concerned about bothering to find that right now. But let's see. At f of 0 is 9, so I'm somewhere up here. At 1/3, right, I'm going increasing to decreasing, so I should have a maximum at 1/3. And then I'm going to 3, and I have a minimum, right, so I'm going from decreasing to increasing. I'm concave down until 5/3. So what that tells me is at 5/3 I change concavity. So this graph, a pretty good estimate, would be something like this, and then it goes concave up to get to those minimum points. And this is the reason why we can tell where the relative extrema are, right? If I'm concave down and I have where f prime is equal to 0, that should be a maximum point, because if it's concave down, then it has a highest point where it's changing direction. If I'm concave up, right, which means I'm curving this way, if I'm concave up, then there needs to be a low point if I have f prime equal to 0. It doesn't continue to go down, because if it were to continue to go down, then that would be an actual point of inflection right now, right there, which would not be a minimum, a relative minimum for that. Okay, so that's kind of how we use all of this information to help us. So while it's a lot, really all we're adding is just this concavity piece to what you already know. All right. Alrighty. So same idea. This one I'm not going to go into that big depth and show the graph or anything. Just determine the intervals on which it is concave up or concave down and find any points of inflection. So let's do our derivatives, right? So f prime would be negative 3x squared plus 12x minus 5 would be nothing. So f double prime would be negative 6x plus 12. 0 equals negative 6x plus 12. That's a 12 or something. Right, so then x would be negative 12 divided by negative 6 is 2. That is what I'm checking around using my second derivative test. Positive 2 is where I could change concavity. So if I check 0 and I check 10, 0 would yield a positive for f double prime, which means f is concave up. 10 would yield a negative for f double prime, which means that is concave down. So x equals 2 is indeed a point of inflection. So I'm going to copy all of my reasoning and change my intervals. This time I'm going from positive to negative though. From positive to negative at x equals 2, right? And I'm concave up from negative infinity to 2 and concave down from 2 to infinity. All right. Notice this time I'm only on the interval from 0 to 2 pi, so that'll be important. Let's do our derivatives. So f prime is cosine minus sine, and f double prime is negative sine minus cosine. And if I set that equal to 0, then I need to have the positions where sine is equal to negative cosine. Essentially, I need to have the positions where sine and cosine have the same value but opposite signs. That's going to be at our pi over 4s, right? But where they have different values. So A, S, T, C, right? They have the opposite sign in those two quadrants at pi over 4. That's pi over 4s. It's some form of root 2 over 2, root 2 over 2 for our unit circle. So I need to have pi over 4s as my solutions. So I'm going to use 3 pi over 4 and 7 pi over 4. And f double prime f. All right, so if I check 0, 0 would give me a, remember I'm checking it into this one, right? That would be 0 minus 1, so this would be a negative interval, which means this is also a negative because I could check 2 pi, and that's the same thing as 0. So I am concave down and concave down. And then if I check pi, let's see, that would be 0 minus a negative 1, which would mean that's a positive 1. So I am concave up on that interval. So I have 2 points of inflection. I have 2 intervals where I am concave down and one where I'm concave up. So I have concave down from 0 to 3 pi over 4 and 7 pi over 4 to 2 pi. Concave up from 3 pi over 4 to 7 pi over 4. Right, and I need to add my justifications because f double prime is less than 0 and because f double prime is greater than 0. And then I have points of inflections. Yikes. Yeah, I'll do that. X equals 3 pi over 4 and 7 pi over 4. Because f double prime goes from positive to, well, we're going negative to positive first, huh? Right, so essentially f prime changes signs at both of those places. Okay. So let's see, h of x is secant on the interval from 0 to 4 pi, so I'm doing 2 unit circles. They're going to do announcements here in just a minute, so I may cut it off as soon as they are talking.
Good morning, Mark.
There we go.
This is Extrema.
All right, this one's a little bit of a pain, but that's okay. We will work through our pain. Work through the pain. Okay, so we have h of x is secant of x minus pi over 2 from the interval 0 to 4 pi. So there's a few things that we need to think about this. Secant has a graph that looks like this. So I have some asymptotes that I'm going to be not differentiable at. So I'm going to need to think about kind of where those are. And the whole graph has been moved right pi over 2, so they should be happening every pi. So at 0 pi, pi, and 2 pi, I will have asymptotes, and even 3 pi, right? But 0 pi won't be included because it's not a part of my interval. Come on, Mr. Pike. All right, so let's get after this, right? So I want to find the second derivative, so take your time. All right, the first derivative would be secant tangent of the angle, and then times the derivative of the angle inside, which would just be 1, which is nice, right? And then I'm going to want to do the derivative of my first derivative to get the second. So this is going to invoke the chain rule, or sorry, product rule. All right, so I'll do the derivative of the first times the second. And the derivative of the first is secant tangent. So secant tangent times tangent should be secant tangent squared. And then plus the derivative of the second times the first. Well, this derivative is secant squared of the angle times your secant would be secant cubed. Look at that. Look at how much time this is saving. This is a miracle. All right, so now, thinking about all of this, this is a pain to try to figure out when this is equal to 0. So what I would like to do is I do notice that both of these things have a secant with them. So if I set it equal to 0 and I factor, all right, that gets me to 0 equals secant of x minus 2. And now since I divided out that secant and I divided out a secant from here, I am left on the inside with tangent squared plus secant squared. Now you're going to need to remember for me that secant squared, let's see, how can I do this? I'm just going to have to write it with my little laser pen. Tangent squared plus 1 is equal to secant squared, right, where I keep my angle. So if that is the case, what I can do with this tangent squared plus secant squared that I have left inside is replace that secant squared with a tangent squared plus 1. And what that will get me to is 2 tangent squared plus 1. And now I have this thing factored, so this thing times this thing equals 0. And I want to see if I can find any zeros. Well, if I set x minus pi over 2, my angle, equal to whatever I want to, right? So I need to figure out what angle I need to put in such that secant would come out 0. It's not possible. Secant's never going to be 0 because it would be 1 over cosine. And if cosine is 0, then that means secant is undefined. So that's not going to happen. So the other place would be when tangent of x minus 2 is equal to, let's see, negative square root of negative 1 over 2 when I solve, which is also not possible. So there's nowhere on this domain that I am equal to 0 for my second derivative. Good afternoon, good morning, Annalise. All right, so again, going back to the only things that I really have to check around are my undefined parts. Secant is undefined normally, right? So all this was useless. I did this for absolutely nothing. Bogus. Stupid Mr. Pike making us doing crap for nothing. Okay, so secant, the parent function of that was related to cosine, where I have asymptotes at every pi over 2. So if I move it to the right pi over 2, to the right pi over 2, then, and now my asymptotes are at pi, 2 pi, and 3 pi, because at 4 pi I will be nothing. I could probably even just base my answer off of this graph, but using that second derivative, which I just erased, so I am glad that we did it, right? But all of this is useless. Go away! Nobody wants you here. You guys all smell funny. All right, but I want to check pi. I want to check around 2 pi, and I want to check past 3 pi. So if I do like pi over 2 or something, that would be secant of 0, which is 1, and then tangent of 0, which is 0. So this would be 1 times 1, so this would be a positive interval for f double prime. F. So that means I am concave up. If I check 3 pi over 2, secant is negative 1 when I plug that in. Tangent is still 0, so this would be a negative. So I'm concave down. Then I go around the unit circle, so I'm concave up again, and concave down because it's just going around the same rotation. All right, so that was positive, and that was negative. So there are no points of inflection. And that is because, right, I am undefined at these values. These are asymptotes. That's how I came up with those values that I'm checking around. So there are no points of inflection because f double prime never equals 0. And then I can state the intervals. I'm concave up, concave down. Concave up at 0 to pi and 2 pi to 3 pi. Because f double prime is greater than 0, and concave down from pi to 2 pi and 3 pi to 4 pi, because f double prime is less than 0. Right, you got to show me the justification on that stuff. Get out of the way, head. All right, so that's an instance where like the second derivative was never equal to 0, so I don't have any points of inflection, but I do have things to check around. And those are your asymptotes, because they will be undefined at those parts. All right, use the second derivative test to identify any extrema. So I think after this, yeah, we're just going to sketch one and we're good to go. All right. So my first derivative, again, what I want to do is I want to show the intervals where it is concave up. It's exactly like that first one that we talked about. So since I was concave down on the interval from 0 to 5/3, this point, when f prime was equal to 0, right, if I am concave down, that had to be a maximum. And from 5/3 on was this portion over here, and that 3, since I'm concave up, had to be a minimum. That's essentially what we are going to do. We are just going to use words to state it. Well, not words. We're going to use math to state it. All right, folks. You have no idea what just happened. But it is the next day, and I screwed up big time. Well, not huge, but I messed up with my justification. So because I'm a horrible teacher, I need to go back and edit things. I made a mistake. Also made a mistake on the next one, which is wonderful, just beautiful. So I'm going to redo both of these junks, not convert to text. I'm going to delete all that junk up in that trunk. And let's get after it. Okay, so still, I was correct. Yeah, I did something right. In saying that essentially, if we can prove that I have a part that is concave up, this would be a minimum value, right? If I have a part that is concave down, this would be a maximum value. So I need to figure out where the concavities are, and also where I have my first derivative equal to 0. So this is kind of a combination with the first derivative test as well, but not too much. I just need to know when it's equal to 0. So let's go ahead and find my first derivative. So it's negative 15x to the 4th plus 15x to the 2nd. The second derivative would be negative 60x to the 3rd plus 30x, right? And so I want to figure out where my concavities are changing. So I'm going to factor out a negative 30x, and then I have 2x squared plus minus 1, right? Yeah. Okay, good. So then I have 0 equals, well, I'll just write my solutions at this point. So x equals 0, and then x equals plus or minus 1 over root 2, which is approximately plus or minus 0.707. So I am going to write out my second derivative test on my number line. Chew. So I have 0, I have negative root 2 over 2, I have positive root 2 over 2, and that's where I want to test around to figure out my concavity. So I have an f double prime that I'm going to relate it to. I'm going to move it over just a little bit. I also have an f that I want to relate it to as well. So moving forward from this point, right, I need to figure out numbers, right? So if I know that negative root 2 over 2 is about 0.707, then I'm going to check like negative 10 and see whether it comes out positive or negative. Again, I'm going to be plugging it into this one here. That is the easiest for me to determine whether it's going to come out positive or negative, just personally. You could plug it into this one as well. Makes no difference to me. But this one, all I really need to do is see if this comes out positive or negative, this comes out positive or negative, and then it's either positive times positive, negative times a negative, positive times a negative, so on and so forth. So I'm just checking signs in this, right? So if I put in negative 10, the first one, that 30x is positive, and then the second one would also be a positive number. So this is a positive interval, so I am concave up. Concave up will look like this. All right, so between here, I would choose like negative 1/2 or something. So negative 1/2 would come out positive times a, be 1/4 times 2 is 1/2 times a negative, so this is a negative interval. So now I'm concave down. Positive 1/2 will be a, if I put in 1/2, that's a negative out front and a negative there, so this is a positive interval. So this will be concave up, and then if I put in positive 10, that's a negative times a positive will be a negative interval, so that is concave down. Alrighty. Yeah. Yeah. Alrighty. So now the other thing I need to do is figure out where my first derivative is equal to 0, right? I need to figure out what are my values that I could even have extrema. Well, that's when 0 equals negative 15x to the fourth plus 15x squared. So if I factor out a negative 15, x squared minus 1. All right, I could have x equals 0 or x equals plus or minus 1. So now see where those fit. All right, 0 is right here where I'm changing concavity. So if I'm changing concavity there, what that means is if this is going to from concave down to concave up, this is doing something like this at x equals 0. It could be the other way around. Well, no, it has to be that way, right? So since it's just changing concavity there, all that means is this is not really a extrema. This is called the point of inflection, right? So it's changing the point of inflection. I have a horizontal tangent there. There's not always a horizontal tangent in point of inflection, but in this case there is. So that is not really an extrema. Now I need to figure out where negative 1 and positive 1 fit on my interval. Well, negative 1 is over here. And if I am concave down there, then that must be a minimum point. Positive 1 is over here. If I am concave up there, or sorry, I just said that all wrong. Boo! I am concave up, so that's a minimum. I am concave down, so that is a maximum. There's so much to keep straight in your head, so just take your time. I'm trying to go too fast for you guys. That's why I like doing notes in class. It gives me time to make sure I say it appropriately for you. Okay. So at x equals negative 1. This is a minimum because f prime is equal to 0 there, and f double prime is greater than 0, right? Since I am concave up, it had a low point on this thing. So since it had a low point, that means I had a minimum. Then at x equals positive 1, I have a relative max because f prime is equal to 0 and f double prime is less than 0 there. Right, because I had a concave down graph, it had a maximum point. That is what I expect to see for all of your justifications. This is not complete without both of these statements. You also have to tell me what kind it is and where it is. So that whole statement right there could be worth 3 points. All right, but that is using the second derivative test to identify any extrema. All right, part B here. Let's try to do this without messing up this time. I messed up the derivative. I believe I explained it correctly, but I messed up the derivative. All right, so 4x to the third minus 12x squared plus nothing, right? And then I also have f double prime is 12x squared minus 24x. So I would like to find when this is 0 to figure out my concavity, so I'll factor out a 12x. So then I have x minus 2, so x equals 0 and x equals 2. I could be changing concavity. So I might as well go ahead and throw those on my number line. So I have 0 that I want to check around, and 2, I want to relate f double prime to f at, say, negative 5. If I put that in, that's a negative times a negative, which is a positive. So that means I will be concave up. Between 0 and 2, I have 1. That would come out a negative, so I will be concave down. And bigger than 2 could be 10. It would be a positive, so I am concave up there. So let's figure out where this thing is equal to 0. I'm going to factor out a 4x squared. So x minus 3. So x equals 0 and x equals 3. Again, since I have 0 as a first derivative, a critical point for my first derivative, and I have it as a point of inflection, all this is meaning is that there's a horizontal tangent there, right? But this is going from concave down, concave up to concave down at 0. So all that's doing is a point of inflection. It's continuously going down. And you would see that with your first derivative test as well. Okay. Choo-choo. So at 3, I really just need to figure out where 3 fits. 3 fits right here. So what that tells me is that would be a minimum point because I am concave up. So x equals 3 is my only relative extrema, and that is a relative min because f prime is 0 and f double prime is greater than 0 there. Alrighty, cool deal. Okay, that should be it. And then I'm going to keep talking about other random stuff. Cool, yay. All right, so last big idea that you guys need to be able to get straight is being able to sketch these things using our first derivative rules and using our second derivative rules. I like to essentially make a table like we did in that one example 2 part A, where I kind of recognize and I think about on my graph everything that is going on. It helps me get my mind straight with what needs to happen before I really get into it. All right, let me pull up a graph. All right, so just going through my characteristics, f of 2 and f of 4 is 0. So that means at positive 2 and positive 4, my y value is 0. All right, so now I'm getting into my first derivative. So f prime is greater than 0 for x less than 3. So 3 is a cutting point, it looks like. F prime is positive, so that means I need to be increasing. Here's another one. All right, f prime is less than 0 for x is less than 3, so that's negative there. And f prime of 3 does not exist. Right, so that's a point of non-differentiability is what that means, right? So it could be a sharp turn, could be a vertical asymptote, depending on what other information we are given, but it is a point of non-differentiability is the big key that you need to pull from that part. All right, and I see I have some that get into my second derivative. My second derivative is always greater than 0, except it cannot be 3. Does not exist because if it's not differentiable before, then it's not differentiable again. So I am positive and positive. So that means I'm concave up and concave up. So let's see, at 3, I can have a sharp turn. I need to be increasing to decreasing, concave up the entire time. Increasing that whole time. So again, a few ways you could look at it. I'm just going to make up a point right there. And if I concave up the entire time, it could be a rational function or something. So I'm going to make it a rational function. So those are always concave up. But I'll make it go to that point. Why not? And then I am decreasing, but still concave up. So I'm going to make some sort of rational function like that. That's weird that it graphs like that. You could also make this a real rational function, right? And have a vertical asymptote that it goes around in both directions. Either way you want to do that, right? But you have to be concave up and increasing on the left side. You have to be decreasing on the right side as well as concave up. So it's really just taking your time and going through those characteristics. Other than that, whatever questions you guys got, let me know, and I will talk to y'all soon.